Hi, this is Michael Borenstein speaking, and this is the first in a series of lectures on meta-analysis. Our website is www.metaanalysis.com. My email address is michael@metaanalysis.com, and thank you for joining us. So in this first part, I wanted to discuss what is a meta-analysis, why you might want to perform a meta-analysis, how a meta-analysis works. One of the things we can do using a meta-analysis is to compare subgroups and why meta-analysis is an especially good way to do that. And then I wanted to spend a few minutes talking about criticisms of meta-analysis. Okay, what is a meta-analysis? I'm going to use an example. This is actually an example from medicine, but you'll find that it generalizes very well to almost any field. I mean, one of the things about meta-analysis is that it's a method like any other method, and you can apply it to essentially any field that you're working in. But this is a study by Canon et al., and what they did was they looked at the impact of statin dose on two outcomes, on death and having a myocardial infarction, the risk of having a heart attack. Now, as I'm sure everybody knows, one of the things that physicians push is if somebody has a high level of cholesterol, they give them drugs like Lipitor or various other drugs with the intent being to reduce the amount of cholesterol, and the thinking is that it's going to prevent people having some kind of a heart incident. And the question is are the statins more effective if they're given in a high dose as opposed to a low dose? And there were a total of 4 randomized clinical trials that looked at this question. The first one was called the Prove It study. I hate these acronyms, but that's actually the way that they were published. One is the A to Z study, one is the TNT study, and one was the Ideal study. And they were done by 4 separate groups of people. They were all very large clinical randomized trials. You can see that in the first one, the sample size was about 4,000. The next one was about 4,500. The next one had about 10,000, and the next one had about 9,000. So these were large trials. What you're looking at in the middle, the schematic, is called a forest plot. And since we're dealing with risk ratios here, are people familiar with risk ratios? It's just so, for the sake of argument, the first one is a risk ratio of 0.84, which means that patients that were given the high dose, you can see the label at the bottom, were only 84% as likely to have a heart attack or die as compared to patients that were given the standard dose. Since this is a ratio scale, the null hypothesis is 1, which is represented by that line in the center, and that would suggest that the risk of dying or having a heart attack was identical in both groups. Anything to the left of that tells you that the risk of dying or having a heart attack was lower if you were given the higher dose. And in each case we have a point estimate, which is represented by that block. In the first case, it's 0.84, 0.86. In the second case, 0.80, and so on, representing on this scale. You notice that the scale only goes from about 0.80 at the bottom to 1.25 at the top, with the lines extending somewhat beyond that. So all of these suggested that having the higher dose was more effective than having the standard dose. But at the same time, each of those points is bounded by a confidence interval, represented by the horizontal line. And that tells you that, for example, in the first case, while the overall risk ratio was 0.84, the 95% confidence interval for that goes down as low as about, well, it's hard to tell, probably about 0.60 or 0.70 at the lower end, up to 1 point something at the upper end. And if the confidence interval includes the null, which it does in this case, that means that we can't rule out the possibility that the actual effect is null, that the actual risk ratio is 1. So it's a tautology that whenever that confidence interval includes that vertical line, the p-value is going to be greater than 0.05, right? If the 95% confidence interval includes the null hypothesis, then the p-value for testing the null hypothesis has to be greater than 0.05. Similarly, if the 90% confidence interval included the null, then the p-value would have to be greater than 0.1. It's simply 2 halves of a coin. And therefore, since the confidence interval for that first one includes 1, it's not surprising, in fact, to find out that the p-value was 0.106. So we have over here a study that indicated a 16% reduction in death rate. It had more than 4,000 people in it, and yet it's not statistically significant. This is a problem that we come across often in primary studies, that the power is low. Even if the effect is clinically important, and certainly a 16-point reduction in death would be obviously very clinically important, and even if the study is reasonably large, and 4,000 is awful large by most standards, we still have only a modest or low power to get a significant effect. That's one of the main problems that we have with primary studies. Similarly, in the second study, the risk ratio was 0.86, again very similar to the first, suggesting a 14% reduction in the risk of death, 4,500 people. The confidence interval includes the null, and the p-value is 0.096, again not statistically significant. In the third study, the effect size is a little bit larger, a 20% reduction in the risk of death. The risk ratio was 0.80. And in this case, the p-value actually is significant at the 0.05 level. It's 0.002, corresponding to the fact that the confidence intervals do not include the null. And the last study suggested an 11% decrease in the risk of death. The p-value, again, is not statistically significant. What we're going to be looking at in this example is that when you do a meta-analysis and synthesize the results of these four studies, we get an estimate of the effect of 0.85, suggesting a 15% reduction in the risk of death, based on about 28,000 patients, and the p-value is well under 0.05. And one of the things that we're going to be talking about, I know that you started discussing last week the idea of effect sizes. What we do in a meta-analysis is we compute an effect size for each study. In this case, it was the risk ratio. It could have been a standardized mean difference. It could have been an odds ratio. It could have been a correlation. It can be anything. And then we assign a weight to each of those based on various things that we're going to be talking about later. But basically, the more precise the estimate, the more weight we assign to that value. Then we synthesize the data. We compute a summary effect and confidence intervals for the summary effect by taking a weighted mean of all of those effects. And that's what we're going to be doing. That's what I'm going to be discussing today. I think you've already discussed the idea that a systematic review is parallel in its goals and its methods to what we do in a primary study. In a primary study, we have an hypothesis. We have inclusion and exclusion criteria for enrolling people in the study. We collect the data. We do the statistical analysis. We write a report. Similarly, in the systematic review, we have an hypothesis. We have inclusion or exclusion criteria for including or excluding studies from the review. We collect data, which in this case is collecting studies and parsing the information. We do a statistical analysis, and we write a report. The statistical analysis that we do in the systematic review is what I'm calling a meta-analysis. And that's what I'm going to be focusing on today, just the statistical part of it, which is actually in some ways one of the easier parts because the other parts involve going out and searching the literature and pulling the data out and so on. This part is relatively simple, but nevertheless, it's a critically important part of the process. Okay. Why would you want to perform a meta-analysis as opposed to simply going out and gathering the studies and reading them and coming to some kind of a conclusion? Well, for me, these are the primary reasons. It provides context, it provides power, and it makes it possible to compare subgroups. And I'm going to show you right now what I mean by that. The first thing is it provides context. This is an actual study that was done by Rawson in 1979, looking at the impact of naltrexone on opioid use. He's working with patients who tend to abuse various drugs. And what they did was they took a number of people, randomized them. Some of them got naltrexone, some of them didn't. And we're looking over here at a standardized difference in means, so that he found that after a period of time, patients who were given naltrexone were about 1/2 of a standard deviation less likely to be using drugs. It's the same idea that we saw before. Now the effect size is a standardized mean difference rather than a risk ratio, but this works the same. Here's the effect. The confidence interval includes 0, so the p-value is 0.136. If you looked at this let's say you're somebody that's faced with the task of setting a policy, and you want to know whether or not to recommend naltrexone as something to use in this case. If it was me, the first thing I'd want to know is this effect consistent, or does it vary? In other words, we're looking at one study over here, which might have used a particular population, a particular dose of naltrexone. Maybe the people were of a particular age. Is it going to be the case, if I go ahead and do a whole bunch of studies, that they're going to look like this, that the effect size is pretty much going to line up in a column, and that all of the studies are going to show that naltrexone reduces the risk of opioid use by pretty much the same amount, something in the range of, let's say, 0.25 to 0.45. Is that what I'm going to be looking at? In which case we know that the effect is consistent, and then our goal is going to be to estimate as precisely as possible what that effect is. Or is it going to be the case that it looks like this, that, you know, if we go ahead and do 7 or 8 studies, that we're going to find that in some of them naltrexone had no impact at all, and might actually have been harmful. In some of them it was moderately effective, you know, perhaps giving these people an advantage of about 1/2 of a standard deviation, and in some of them it was incredibly effective. So that if we're looking at some studies over here, the people that were given naltrexone were actually a full standard deviation or more less likely to be using drugs after a period of time. Because this would be a very different take-home message. If this is the way things looked, then it would not be terribly informative to say that on average it reduces the risk by 0.45, or it improves your likelihood to be off the drug by 0.45. Rather, the take-home message over here would be that the effect varies depending on a bunch of other factors, and we probably want to go out and figure out what those factors are. So that would be the logical question that you'd want to ask. And you can't, in general, in fact, almost always, you can't answer that kind of a question by looking at a single study, because by definition, it is a single study. This happens to be the way things actually turned out. These are, on the previous 2 graphs I showed you, Rawson followed by a series of hypothetical studies. These are actually the studies that were done. And the take-home message seems to be that the effect is somewhat consistent. There probably is some real variation in there, but in most cases, the effect seems to fall within a reasonably narrow range, with one exception. There was one study out there that had a much larger effect. But the point is not to focus on the specifics. The point is that this is the way, when you look at this, knowing nothing about naltrexone or opioid use or anything else, you immediately have context for that study. You're looking at a series of studies, and you have a pretty good sense now of how useful this drug is going to be, and how you might want to pursue it. Whereas you can't get that context looking at any one study at a time. The second thing is that it provides power. If we go back to the example that I showed you a minute ago, we had 4 studies. 3 of them had p-values that were not statistically significant, despite the fact that these were enormous studies and probably cost many millions of dollars apiece and took many years to perform. In fact, the problem would be, you know, if somebody went ahead and published these 4 studies without doing a meta-analysis, the take-home message would probably be, well, there were 4 studies that were done. 3 were not statistically significant. 1 was statistically significant, and therefore the jury is out. I actually had, I think I might have told the story a couple of years ago, but it's a true story. When I first started working in the field of meta-analysis, I was looking at a meta-analysis that had been done by Antman, Chalmers, Lau, and some other people that was published in the New England Journal of Medicine, looking at the impact of streptokinase. That is a drug that they started using as far back as the late 1950s. I think the first study was done in 1959. And patients that were given a heart attack, they get to the hospital, they give them an infusion of this drug which is meant to dissolve the clot. So if the thing causing the heart attack is the fact that there's been a clot preventing the flow of blood to the heart, and you're able to dissolve it, the thinking would be that it would improve the, you know, you get the blood going to the heart, there's less damage done to the heart muscle, and the prognosis is improved. So there were a total of 33 studies that were done looking at that over a period of more than 30 years. 6 of them were statistically significant, and 27 were not. Pretty much the same ratio as you see over here. And I happened to be at my cardiologist doing the stress test, and I'm standing there in my underwear running on the treadmill, and he's controlling the knob. And he said, what do you do for a living? It's like when you were at the dentist and you have this thing coming out of your mouth and they start asking you about your family, and you can't. But they do that. And he was doing the same thing. He says, what do you do for a living? And I said, well, I do meta-analysis. And he says, yeah, what's that about? And I mentioned that since he was a cardiologist, I mentioned the streptokinase study. And he says, yeah, all of the evidence suggests that doesn't work. He says, the vast majority of studies suggest that it doesn't work, but I use it anyway because I know that it saves lives. And now they've actually moved on to other drugs of the same sort. But I'm not going to tell the guy he's misinterpreting those studies because he's controlling the speed, and we're already at about 7 miles an hour, which is 2 miles an hour faster than I can go. But the point is, if you have a study like this one, which is not statistically significant, the interpretation is that we have not proven that this works. The interpretation is not that we've proven that it doesn't work for the reason that we see over here. And yet, the overwhelming majority of clinicians interpret that as meaning that there's evidence against the effectiveness. That's been the case going back at least 40 or 50 years. So the take-home message in a case like this is that 3 of them suggest that it doesn't work. 1 of them suggests that it does. And the problem is when you take something like this and look at it in a narrative review, which basically means some expert goes out there, reads these 4 studies, and then writes a review, when somebody's doing that, they tend to work with the p-values. In other words, they say, well, I have 3 studies over here against, 1 in favor. Therefore, the conclusion is, well, there's certainly not strong evidence. Maybe it works, maybe it doesn't. Or some of them might conclude that that the evidence suggests that it doesn't work. They're doing something called vote counting. They're saying there's 4 studies, 3 of them are against it. And that's the wrong thing to do. And the reason it's the wrong thing to do is, as we see over here, to count this as a vote against is to basically take what that cardiologist was doing and to codify it. He's saying that this is evidence against, this is evidence against, this is evidence against, this is evidence in favor. But in fact, these are not evidence against. These are studies where it's possible that the effect over here was actually nil, or it's possible that the effect was actually substantial and we simply have too small a sample size. And what you're doing in a meta-analysis, whereas the narrative reviewer starts with these conclusions over here, basically they're starting with words and trying to do arithmetic on them. What we're doing in a meta-analysis is we're not starting with these conclusions, as it were. We're starting with the effect sizes. We're going to take a weighted average of them. We're going to take all of the information that's over there, get the most precise estimate that we can so that we're going to have a narrower confidence interval. You see over here, this is more narrow than in any of those. And we'll see in a few minutes why that's the case. And then we're focusing on this. So we're working with effect sizes rather than p-values, which is really what we should be doing. As a matter of fact, I forgot I had this. If you actually go back and compute the power for each of these studies, you'll see that for the first study, the power to get a statistically significant effect was only 36%. In other words, if the true effect size is 0.85, which is what we're concluding at the end of the day the true effect size probably is, based on all of the information, then the chances of getting a significant effect with a sample size of 4,200 patients is only 36%. In the second study, the power was only 39%. Even in this one, where we happen to be lucky and get a p-value of 0.002, the power was only 70%. And over here it was 65%. So in light of that, it's not surprising that 3 out of the 4 studies did not yield a statistically significant effect. Not only is it not surprising, but you could have made that prediction. In fact, the power for the entire set of 4 with 27,000 patients is only 83%. So in a way, we're lucky. I mean, it's possible we could have done this and still gotten a non-significant p-value at the end. But clearly, the power for the 4 of them together is much better than the power for any one of them alone. The other thing that you can do with meta-analysis that you often cannot do with a primary study is to look at different kinds of subgroups. For example, you can look at variance of the intervention, variance of the kind of patient, variance in the follow-up time. And the reason why you can often do this in a meta-analysis and you cannot do it in a primary study is simply that any single primary study is not going to have that many variants in it. And I'll give you for an example, I'm not sure if people here are familiar with antipsychotic drugs or not, but for a long period of time they had what they called first-generation antipsychotic drugs. Haloperidol was one of the main ones, and it worked in many ways, but it also had some fairly serious side effects. So over a period of time, physicians and drug companies developed what they call second-generation antipsychotics, of which there are now about 10 or 11. And one of the things they did was they went back and compared them to haloperidol. So for example, if we're looking at the first one, let's not look at that one because I don't know how to pronounce it. Let's look at the third one, clozapine or clozapine. I guess I don't know how to pronounce that one either. But over there, the risk ratio was 0.17. And the outcome over here is Antiparkisonian. And what this means, one of the side effects of haloperidol was that it would often cause people to start shaking. And if they did that, they would then have to be given Antiparkisonian drugs to counteract the shaking. So to the extent that these new drugs are less likely to cause that, the patients are less likely to need this antidote, as it were. And it turns out that all of these are better than haloperidol in this respect. Over here, the null hypothesis, the risk ratio of 1 would indicate that both drugs were equally likely to require this Antiparkinsonian. The ones to the left mean that patients on the second-generation antipsychotics were doing better. And you can see over here that if you synthesize all of them, you end up with a risk ratio of 0.49, which means that they were only half as likely to need the drugs. And you can see how incredibly precise that estimate is. I mean, that's really what you can do with a meta-analysis. But another question might be, okay, all of them work, but some of them work better than others. In other words, is this over here better than that? Or is this over here better than that? You can begin to address these kinds of questions. We'll spend some time on this later, and I'll show you how to use the program to do that. And obviously, it's not simply a question of, is one of those differences statistically significant and the other one not? It becomes a question of basically doing a comparison of this versus this, or doing an analysis of variance of all of these against each other, where that answer is going to depend on the distance between them and how precise these estimates are. But the point is you can do that. We're dealing over here with a total of 8 studies for the first drug, another 4 for the second, 3 for the third, and so on, so that altogether we probably have about 50 or so studies that we're dealing with. You can't do this kind of comparison using any single study because each study looked at one drug, so there's no way within that study to compare two drugs. And that's generally going to be the case. While, of course, in theory it's possible to do a study where you incorporate 2 or 3 drugs, the sample size is going to be so large that generally people are not going to do that. In fact, I think it's often the case that these studies are sponsored by the particular drug company that's manufacturing the drug, so that in every case they're being compared against haloperidol. It's rare to see head-to-head studies where these drugs are compared against each other. But using a meta-analysis, you can go back and do those kinds of comparisons I was outlining a minute ago. In this case, by the way, that p-value of 0.004 is not the p-value for comparing this against the null. It's the p-value that asks about the dispersion among those different effects and whether or not some of these drugs were more effective than others in preventing anti-Parkinsonian symptoms. This is another outcome that they looked at, which was sedation. The point over here, these, by the way, I think these graphs are adapted from a fellow named Stefan Leucht, who worked at Hillside Hospital for a while, and now he's back in Germany. But what you're getting over here by doing this kind of comparison, not only were we able to break this down by drugs, but we're also able to break it down by outcomes. So we can ask whether one drug is more effective than another for this purpose, for this purpose, for this purpose. So basically what you're getting is a whole tapestry. You're getting the kind of information that you want if you are a clinician and trying to give advice to a patient, or if you're a patient and trying to figure out which of these drugs is going to be most effective for you. As compared to, think about what you'd be doing if all we had were primary studies. If we didn't have this kind of a synthesis, how difficult it would be to pull this kind of information out. Over here in this example that I showed you a minute ago, we have 13 studies looking at the first drug, 5 at the second, 23 at the third, and so on, so that in the meta-analysis of that first drug, the effect size that I gave you in the confidence interval was based on 1,000 patients for the first drug, on 2,000 for the second, on 2,000 for the third, and so on. If we had 1,000 patients in the meta-analysis and 13 studies, that tells me that the average number of patients in any single study was only 78. And think about the power that you get when you're working with 1,000 patients versus 78, and how much more precise each of those estimates was. Okay? So let me give you one more example. I said that you can use meta-analysis to put these things in context and to compare subgroups, which generally you can't do in any single study. As I was looking, I was looking for examples of this. This goes back a couple of years. I happened to be at the Cochrane meeting. People familiar with Cochrane? Cochrane is an organization that does meta-analyses in the medical field. So they come out with not so much recommendations, but they come out with syntheses looking at many different diseases. They have about 54 working groups in neonatology, in cancer, cancer of the brain, cancer of the back, cancer of bones, and and headaches, and just about in most of the important medical fields, depression, and they do meta-analyses and then publish that so that physicians who want to be working with the best evidence have access to that. Well, this meeting happened to be in Singapore, and I was traveling back to the States, and I had to give a talk on subgroup analyses at NIH when I got back. And so obviously this was the time to start preparing it because it was a long flight. And I sat down at the airport in Singapore, and it turns out that they have free access. Not only has anybody ever been to Singapore? Things there actually work. So the airport has free access to the internet with like broadband speeds. They have free access to the Cochrane Library, which normally requires a subscription. And it only takes you like 3 minutes to get through security and passport control. So I had an hour to sit there and work on my talk. And the first thing that I did was I logged into the Cochrane Library and started downloading every meta-analysis that used subgroups. And then I got into various other databases so that by the time I got onto the plane, I had all of these PDFs with me and I could work on it on the flight. This is one of the ones that I found. It was psychological approaches in the treatment of specific phobias. And I started looking at it, and I'm reading this, and it says, somebody came up with a way of dealing with these different kinds of phobias, this fear of enclosed spaces. It says over here, one of the most common anxiety disorders, fear of heights and fear of snakes. And I said, oh my God, I've seen this someplace before. And I remembered having seen this cartoon. The caption is Professor Gallagher and his controversial technique of simultaneously confronting the fear of enclosed spaces, heights, and snakes. I say, yes. And this is his way of dealing with it. The idea is you're supposed to expose people to their fears and they'll be able to conquer them. So you have Professor Gallagher. Here you have a guy who's confronting his fear of heights because he's hanging from a 5-story building, his fear of enclosed spaces. He's locked into this phone booth. And of course, there are the snakes wrapped around his neck. And that's a close-up of the guy. And this, of course, is Gary Larson. People here are all too young to remember Gary. I was at a CS. People here know who Crosby, Stills, and Nash are? I mean, I was at the concert last night. First of all, everybody in the lobby was getting stoned. And these are all people in their 60s and 70s. And I heard one of the guys saying, I don't really want to get stoned, but I sort of feel obligated, because when these guys first came around, when they were, I guess, in their early 20s and all the people in the audience were in their teens, I mean, that was the only way to appreciate the concert. But then I heard one of the people explaining to the ushers who Crosby, Stills, and Nash were. He says, imagine like Justin Bieber, except in the 60s. I mean, they had no concept of, and I guess the joke would go over bigger if you guys actually knew who. Have you heard of the Beatles? It's never mind. Okay. Anyway.
I've given up trying to make that kind of connection.
I appreciate it. There's a great line in this movie with Jim Carrey and somebody where some of them saying, you ever heard of the Beatles? He says, yeah, those are the guys that ripped off the Monkees, right? So anyway, okay. So here it turns out there actually was science behind this, although I guess my main reason for showing it was I thought I could get you guys to laugh. But it turns out that in these, when they're doing these exposures for phobias, that the immediate reduction is 0.38 as a standardized difference in means, and the follow-up, I don't know if that was a year later or 6 months later, was only a little bit smaller, so it suggested that the impact, whatever it was, lasted over time. So here we have subgroups, not in the sense of different populations or different interventions, but in different lengths of follow-up. The point is, this is a method. You can use it for almost anything. How a meta-analysis works. Okay, I showed you over here this example before. I mentioned that we compute an effect size for each of these. We take a weighted mean of them when we come out with the synthesis. The way that we do that, let's say we had a meta-analysis, to sort of misuse the term, with only one study. And that was the effect size and that was the confidence interval. And we did a meta-analysis, which we're showing down here as this diamond. The results that we get over here are going to match exactly the results that we had for that single study, which is pretty good, because if it didn't work that way, then we'd be in trouble. The way that we compute the overall effect is we take a weighted mean. So the variance for each of these, I think you started to discuss this last week when you were talking about computing effect sizes and their variance. The variance is going to be, it's going to depend on whether we're working with a standardized mean difference or a log odds ratio or whatever it might be. But once we have that variance, we want to use that in assigning weights. And we don't want to weight by the variance, because then we'd be giving more weight to the studies which have more variance and therefore are less precise. Rather, we weight by 1 over the variance, the inverse of the variance. And what happens then is we're giving more weights to the studies which are more precise. So in this case, the way that we do that is we compute the sum. We take the inverse variance, 1 over that gives us the weight. In the first case, the variance is 0.08. 1 over that gives us 12. And that's going to be the weight that we assign to the first study. So the formula is the sum of each weight times its effect size. 12 times 0.5, which was the effect size over there, gives us 6.06. The sum of the weights is 12. So 6.06 over 12 is 0.50. And that's the effect size that we get over here. And in this case, all that we've done is recreate the original effect that we had. Then the variance of this, or the standard error, is going to be 1 over the sum of the weights. I find it's very helpful, you'll see where this goes in a couple of minutes, to think of the weights as the amount of information that's being given to us by each study. And so if the total weight that we have, the total amount of information that we have is 12.12, then the variance of that estimate, the error in that estimate, is going to be 1 over 12.12, which is 0.083. The standard error of that, the same as we have in a primary study, if we have the variance, the standard error is going to be the square root of that. So the standard error is going to be the square root of 0.083, which is 0.287. Then we can plot the combined effect, which is 0.5, plus or minus 1.96 times the standard error, gives us this confidence interval, which, as I said, turns out to be exactly the same as the one that we had up there. Okay, so far nothing very exciting. But what happens when you add a second study? Now we have twice as much information. So now the formula gives us 12.12 over 24.24, which is again 0.50. But look what happens to the variance. Instead of being 1 over 12, it's now 1 over 24, which is exactly half as much variance. Therefore, the standard error is going to be more narrow. It's going to be 0.20, whereas before it had been some larger number. I don't recall exactly what it was. But look what happens over here. This confidence interval is now more narrow, whereas before it had gone from here to here. Now the variance is only 50% as large. Therefore, the standard error is only, well, whatever it is, the square root of 50% as large. Or, well, you know what I'm getting at. And therefore, we have a more precise estimate. And we add another one, and it becomes even more narrow, and another one, and another one. So by the time we have 5, the amount of information that we have, rather than being 12, is now 60. The variance is only 1/5 as much as it had been. The standard error, again, is only a fraction of what it had been. And look at how precise this estimate is now compared to what it had been before. And that's what we're doing as we add more and more information, provided that the effects are all consistent with each other. Okay? So far we're dealing with what, in effect, is a fixed effect model, which means that all of these are estimating pretty much the same thing. Everybody with me so far? Okay. And another way to look at this, Since we're dealing here with a situation where the effects are pretty much all the same, in theory there are two kinds of error, or two kinds of variance we would need to deal with. One is the imprecision of each study. In other words, if you have a study which is not terribly large, the effect size that we get in that study is only an estimate of what really should be the effect in that population. The second kind of variance we need to deal with is the fact that the true effect size might vary from one study to the next. So if we're looking at something like, let's say, the impact of some intervention on SAT scores, you can imagine that that impact is going to vary from one study to the next, because some studies used patients that were higher SES, lower SES, older, younger, whatever the reasons might be. And therefore there's not, excuse me, there's not a single true effect size, but there's a series of true effect sizes, each study having its own true effect size. So the first source of variation that we have is that we are misestimating each effect size. The effect size that we're taking out of each study is not exactly the same as the true effect size in each study. But the second source of variation is that even if we actually knew the effect size for each study exactly, let's say each study had 1 million kids in it and we had a really precise estimate of the true effect size for that study, that we're sampling only 5 studies from potentially 1,000 studies that could have been done. And the true effect size, the true mean of these 5 studies is not the same as the true mean in all possible studies. We might have sampled disproportionately from lower SES neighborhoods, and therefore we might be estimating an effect size in those neighborhoods, but not across all neighborhoods. And therefore that's the second source of variance. In this case, because all of the effects appear to line up pretty much in a column, we're saying that the second source of variance, the fact that the effect size, the true effect size, can vary from one study to the next, is 0. So the only error that we're talking about is the error within each study, the fact that each study has a finite sample size. And in that case, when we're coming down here, the weight assigned to each study is going to be 1 over this, or it's going to be 1 over the within study error plus 0, because there is no second source of error. When we come down to the bottom, we have a very precise estimate, because the only source of error was this 0.083 variance within each study. And as we get more and more studies, we're able to eliminate that. That's going to become smaller and smaller. But here's a different situation. Let's say that the 5 studies, rather than all having precisely the same effect size, the effect size varies. In the first study, it's 0, then it's 0.25, 0.50, 0.75, 1.0. Okay, you see that? Look what happens now. The first thing is, what we're seeing is a situation where if we've sampled 5 studies at random and we get this much variation among them, this tells us that the true effect size actually varies from one study to the next. And once we know that the true effect size varies from one study to the next, then we have to acknowledge that there's this second source of imprecision out there. And if there is this second source of imprecision, then the problem is if we've only sampled 5 studies from this distribution of effect sizes, then we don't have a really precise estimate of what the true effect might be. Even if each of these studies, let's say that each of these had a really, really narrow confidence interval, so that the confidence interval almost essentially disappeared, we still would not have a really good estimate of what the overall mean effect is, simply because it's the same way like if you did a primary study and had only 5 subjects in it, you wouldn't have a really good estimate of what the effect is. If there are potentially an infinite number of populations out there, and the effect is going to vary one from the next, and you've only sampled 5 of them, then you can't possibly have a really good estimate of what the overall effect might be. And the more variation there is, the more imprecision there is, and the more studies you need to get a good estimate of the overall mean effect. The same way as you would in a primary study. Let's say you're trying to estimate the mean SAT score among a group of students. If all of them have pretty much the same SAT score, and you know that going in, then you can probably sample only 20 or 30 and get a good estimate of the mean. But if their SAT scores vary all over the place, then you're probably going to need 50 or 100 students to get a good estimate of what that mean is. So in this case, we're saying that there are 2 sources of variation. It's not the case that each of these confidence intervals is very narrow. That's one source of error, is that we have an imprecise estimate of the true effect in each study. The second source of error is that the true effect actually varies from one study to the next. So if what we're trying to do is to use each of these studies as an estimate of the overall true mean, then the imprecision is going to incorporate this source of variance plus that source of variance. So if you're thinking about how much information we have, where we're talking about information as how well we can estimate some number, it's no longer 12 for each of these. Now it's only 6 for each of these. In this particular example, these two things are relatively comparable. The first source of variance is 0.08. The second source is 0.07. So we have twice as much imprecision, twice as much variance when we add those two things together, and therefore the weight is only going to be half as large. Let me jump ahead for a minute and show you. I can show you this over here. In the first case, we're talking about the situation where the effects are all the same. And let's say that we know this for a fact, that all of them have the same true effect. So we're trying to estimate this value over here called theta, which is a common true effect. So the true effect size for this study is here. The true effect size for this study is here. By definition, they're all the same. And as it happens, the sample estimate, the study gives us an effect size over here of this and an effect size over here of this. The distance between this and this is purely within study sampling error. And because in this case we had a large sample size, we have a relatively precise estimate. Because the sample size is large, we know that the sample estimate is going to fall pretty close to the true estimate. This is a study where the sample size is smaller, therefore there's more sampling error, and in this example the study effect size happened to fall quite some distance from the true effect. But what we know for a fact in this situation is that the only source of error is the distance between here and here and between here and here, because we've said going in that all of the true effect sizes are the same. By contrast, and that's why, by the way, so the variance is simply 1 over this, and the variance here is 1 over that. When we come to the random effects model, the situation where the effect size might vary, corresponding to the chart that I was showing you a minute ago, now there are two sources of error. It's no longer the case that what we're trying to estimate is theta, which is a common effect size. Rather, we're saying that there's a mean effect size, which in this case is 100, but the true effect size in any single study might be as low as here or as high as here. In that case, let's say we happen to sample one study over here. The true effect size in this study is over here. The true effect size in this study is over here. So and what we're looking at is this observed effect and this observed effect. If we're trying to use this to estimate this, there are two sources of error. The first is that this is not an exact estimate. This is not the same as this. That's one source of error. Within the study, we're misestimating the true effect. And the second source of error is that this is not the same as this. So if we're using this to estimate this, the imprecision comes first of all from this variance over here, and second of all from this variance over here. So if we want to figure out how imprecise that is, we take this variance, add it to this one. Those are the two sources of variance. We take 1 over that, and we get an estimate of how much information the study is giving us. Is that clear? Okay. So coming back now to here, that's exactly what we've done. Over here, we're saying that 0.083 represents that curve at the top, which is the misinformation or the imprecision of the distance between the square and the circle within each study, and the 0.07 is the imprecision that we get from that curve at the bottom, which is the distribution of the true scores. Is that clear enough? Okay. So what happens over here now, you'll notice that as we go from this one over here to this, look at that diamond at the bottom, whereas over here it had been pretty narrow, suddenly it gets wider, representing that additional imprecision. And if we go one more, and now we spread out these effects even further, so that rather than going from 0 to 1, they go from minus 0.5 to 1.5, that diamond becomes even more imprecise, even wider. Okay, you see that? And in this case, the variance between studies is 0.51, so that the variance for the first study is going to be 0.08 plus 0.51, And the weight, the amount of information that study is giving us, is now down to 1.6, whereas before it had been 6.6 over here and 12.12 over here. That's basically what we're going to be doing. And if you go back later and follow these computations, you'll see that we have the sum of WY, which is the sum of each weight times its corresponding effect size. We get 4.09 divided by 8.3, which is now the sum of the weights. So again, the overall effect is going to be 0.49. And there's actually a reason why it's 0.49 rather than 0.50, but we don't need to get into that right now. Larry can explain that next week. It's because D is included in the standard error. But the bottom line is that when we take 1 over the sum of the weights, we're getting a much wider variance than they had before. However, there's one more critically important thing. You'll notice that little curve that I have there at the bottom representing tau. You know, Larry's spoken about tau square, which is the between studies variance. The square root of that is tau, which is the between studies standard deviation. Remember at the beginning I showed you that example of Rawson, and I said if the effects are all consistent, what we want to do is to estimate the mean effect as precisely as possible. But once it turns out that the effects vary, we're not solely interested or even interested in estimating the mean effect. It becomes as important, or maybe even more important, to estimate the heterogeneity. That curve over there is meant to estimate how the true effects actually vary. So in this case, what we're saying is that it's not only important to know that the overall effect is 0.5, but it's important to know that the actual effects might vary from a low of actually less than 0 to a high of about 1. And in this case, we're saying that the true effects vary even wider. And we can basically look at that distribution. And the same way that if you were doing a primary study, let's say this was not a study to look at the impact of an intervention, but simply a study to assess to get the mean SAT, the mean GPA for a group of students, you don't want to know only what the mean is. You also want to know what the standard deviation is, because you want to know how much variation there is. I mean, that's obviously a very basic point in trying to describe what you're looking at. Similarly over here, one of the things that we're doing is reporting what that standard deviation of true effects is. Because that, just like you would in a primary study, you need to know that to know how the intervention is working. 2 interventions both have a mean of 0.5, but in one case, the dispersion of those interventions is very narrow. That tells us that the effect is consistent. In the second case, it varies somewhat. In the third case, it varies substantially. Obviously, a drug that on average reduces the risk of death by 50%, and across all studies that ranges from a 40% reduction to a 60% reduction, is very different than a drug that reduces the risk of death by 50% on average, but in some cases increases the risk of death by 20%. Those have very different implications. I said before that it helps me to think of the weights. If you're looking at these weights over here, there's 2 parts that are critically important. One is it gives you the total amount of information that each study is providing. The second thing is that it tells you the relative amount of information that each study is providing. In this theoretical example, because I was trying to make certain points, I set this up so that each study has the same number of subjects and each study has the same confidence interval. But what you'll see as we get into other studies in a few minutes, that it's often the case that some studies are larger than others, therefore they provide more information, therefore they're given more weight in the analysis. So what we're going to be getting out of the weights as we proceed today is not only the total amount of information, but the relationship between those. If one has a weight of 6 and one has a weight of 12, the second study has twice the amount of impact on the weighted mean. Under the fixed effect model, because the only source of error is within study error, if you happen to have one study which is very large, like the donut study over here, and another study which is small, like the, let's say, the Stewart study, the large study is going to get a lot more weight. So we're going to give the lion's share of the weight to the large one because it just has much more information. By contrast, when we move to a random effects model, the studies all get more balanced weights. In this case, donut is still getting more weight than Stewart, but the ratio is much smaller. If you think of the area of each of these boxes as the amount as the weight, in this case, donut looks like it's getting about 5 times as much weight under the fixed effects, Whereas under random effects, it's only getting maybe 3 times as much weight. And the reason for that, if you think about this logically, if you're saying a priori that all of the studies are measuring exactly the same thing, then logically, the amount of weight that each one gets has to be proportional to how much variance each study has. I mean, think of it like, let's say you have a study. Let's take a case where you're trying to estimate a single number rather than a difference, just to make things a little bit simpler. You have 1,000 students. You get the SAT score for each one. And then just to be difficult, we take that and we pull out 100 students and put them in a separate group. We have the mean for that 100, and then we have the mean for the first 900. Now you have to recreate the mean for all 1,000. How do you do it? Well, the only logical way to do it is to take the first mean, multiply it by 9, the second mean, multiply it by 1, take those two numbers, and you get the weighted mean. And you're going to recreate exactly what you would have had if you took the entire original sample. And that's, in effect, what we're doing with the fixed effect model. We're saying that all of these are estimating exactly the same thing, and therefore, if you're trying to recreate the true mean, you simply weight each one by the variance, which in the other, if we're dealing with some effect sizes, that's simply weighting it by the sample size. By contrast, when we're dealing with a random effects model, while it might be true that Donut has 5 times or as many people as Stewart, but there's a second source of error over here. Let's say, for the sake of argument, that Donut happened to be a study that was sampled just by random error that was way off to the right. And let's say it had 1 million people in it. Okay, that's fine. So we know this. We know the effect size in Donut exactly. But that doesn't tell us what the effect size is for all possible studies. If what we're trying to do is to get the estimate, let's come back over here for a second. If what we're trying to estimate is this mu over here, and we happen to have one study which is way out here and it has 1 million people in it, we might know the mean of that study precisely, or the effect size in that study precisely, but we don't want to give that 99% of the weight because it just happens to be one study that was sampled at random from a whole universe of these. So under the fixed effect model, we would. If we're saying a priori that all of these are estimating the same, that the true effect for all of them is exactly the same, then yes, then we would give that 99.9% of the weight. But under the random effects model, where that's estimating the true effect in one study from among any possible number of studies, we don't want to do that. So what happens is, the net impact of that is that in the fixed effect model, weights can be extreme. A large study is going to get a lot of weight. A small study might get only a trivial amount of weight. Under the random effects model, a large study is not going to get quite as much weight because even though we know the effect size in that study precisely, we still have that second source of error that we're not dealing with. And conversely, a really small study is not going to get only a teeny amount of weight because while there might be, our estimate in that study might be imprecise, but it's the only study that we have that dealt with that particular population, and we don't want to throw that information away. Okay, let me just spend let's say 5 minutes talking about criticisms of meta-analysis, and then we can get on to the program. This is a fellow called Charles Mann, who wrote the book 1491, and I think recently wrote a book called 1493. I guess it's like the Traveling Wilburys, volume 1 and 3. I'm sorry. Larry, you can laugh. Probably, but George Harrison, anybody hear of him? God. Okay. He wrote back in 1990 when meta-analysis was first becoming, I guess, a new technique. He explained why it was potentially important, and he used the example of Fergie, not the Fergie that you guys know, who I understand is a rock singer, but this was like I don't know, not quite the Queen of Duchess of York. There it says right over there. In any event, this was before she was also a spokesperson for Jenny Craig. Do I have the right person? Okay, good, thanks. She was going to have a baby, and the question was whether or not, apparently the baby was presenting breech in the breech position, and the question was whether or not to use a cesarean section. And what he says in this, he's really an excellent writer, but so he sort of brings this home by using an example. It's always good to use an example. In most cases, it's also good to use a joke, but not today. So like many obstetricians, the royal accoucheur treated the princess's breech presentation by cesarean section, and he goes on to explain that the question of whether or not to do that had been debated for hundreds of years. But he says that for the first time they actually have evidence about whether or not a cesarean section is more effective than trying to turn the baby manually. A remarkable report published at the end of last year in the UK offers a window into the possibilities raised by meta-analysis. Effective care in pregnancy and childbirth is the most extensive collection of meta-analyses yet compiled. And he goes on to say that it runs about 1,500 pages, summarizes the results of more than 3,000 randomized trials, and cost $400. The book has triggered an extraordinary range of reactions in the medical profession. Thomas Chalmers says meta-analysis is the wave of the future. The days of the experts supposedly putting the state of the field into a review article are numbered. And the Medical Journal of Australia described it as arguably the most important publication in obstetrics since William Smellie wrote a treatise on the theory and practice of midwifery in 1752. But it was denounced by the editor of the Journal of Obstetrics and Gynecology, who said the price of £225 should protect aspiring residents from acquiring too many confused ideas from its pages. And one doctor called its authors an obstetrical Baader-Meinhof gang. Now here I probably do need to explain. How many people know who the Baader-Meinhof gang was? There you go. Okay, not bad, considering. Okay. Right, we actually had one person that raised their hand. Baader-Meinhof gang were a bunch of people led by somebody called Baader and I think somebody called Meinhof. And what they used to do in the 70s was run around airports in Europe with machine guns, killing as many people as they could. And by calling it an obstetrical Baader-Meinhof gang, essentially he's comparing meta-analysts to terrorists and saying that what these guys were doing on, in airports, these guys are doing with clinical trial data. Somebody else called Alvin Feinstein called meta-analysis statistical alchemy for the 21st century. Somebody called Eysenck, a major psychiatrist named Eysenck called it an exercise in mega-silliness. Samuel Shapiro wrote an article called Meta-Analysis, Schmeta-Analysis. I can't believe this. I'm leaving. Hannah gave this talk in Israel, and she was afraid that people wouldn't know who the Three Stooges were. So the night before, I had to get on the internet and find the Israeli equivalent of the Three Stooges to make the point so that there would be some cultural reference and people would be able to laugh. In this class, people don't know who the Three Stooges are. When I raised my kids, they don't know, how to fold a napkin. They don't know which side. They know who the Three Stooges are because from a young age, you know how the people had like those little things that would twirl around, and the kids like supposed to poke at them like a little cow and a little clown. My kids had videos of the Three Stooges going. They know who these guys are. And it's your assignment for next week to find out. But in any event, you should probably be able to get the idea. The point is, this is the way people, these critics were thinking about meta-analysis. But the criticisms, while there are many of them, can basically take three general routes. One of them is that you can't summarize the results in one number, the results of a whole set of studies. Another one is that you're mixing apples and oranges. And the third is that meta-analyses are performed poorly. So somebody named John C. Baylor III, who I think at the time worked at the University of Chicago and was the editor of the New England Journal of Medicine, wrote in an editorial that any attempt to reduce results to a single value with confidence bounds is likely to lead to conclusions that are wrong, perhaps seriously so. Okay, this is my last joke. Does anybody know who this is? Anybody? Larry. There you go. Who is that? Okay, give that man an A. Okay. Okay, the criticism was, the problem that people have, the number one criticism that I have when I go to lecture on meta-analysis is that people say you can't take a whole body of literature and summarize it in a single number. Okay? Now what this has to do with Clouseau is that in, I think, the fifth of his movies about Inspector Clouseau, he's trying to get a room in an inn in Switzerland. And he says to the guy, have you got a room? And they go through a whole back and forth, and finally he explains to him what a room is. It's a Zimmer. And then as he takes the key and he's about to walk upstairs, he sees standing next to the innkeeper is this cute little dog. And he's about to bend down and pet it. Then he thinks better of it, because he's no idiot. Well, anyway, he thinks better of it. and he says, "Does your dog bite?" And the innkeeper says, "What?" He says, "Does your dog bite?" And the guy says, "No, my dog does not bite." So he bends down and tries to pet the dog, and the dog tries to rip off his arm. He rips off, he bites his hand, he rips off his sleeve, he devours his hat, and finally Clouseau extricates himself, and he's trying to regain his dignity, which is not all that good to begin with. And he says to the guy, "I thought you said your dog does not bite." He said, "My dog does not bite, but that is not my dog." The point is that Baylor is right. Any attempt to reduce the results of an entire field of literature to a single number would be absurd, but that is not the goal of meta-analysis. I think the point that I started out with, and that I'm sure Larry has emphasized to you many times, is that what you're trying to do is to do a synthesis. You're not going in by rote and computing a weighted mean. You're doing a synthesis. You're trying to see if the results are consistent or not. If they are, then you want to go back and use the information to get a more precise estimate of what that effect is. But if they're not, you want to take advantage of their variation, to understand how the studies vary, to try to see if it's possible to explain why they vary. Why is it that this drug in some cases reduces the risk of death by 50% and in other cases increases the risk of death? So that's what you're doing. You're not trying to focus on the summary at all in some cases, or certainly not as the primary thing. The meta-analysis provides context. It tells you if the effect is robust or if it varies. And if it's robust, then you get a more precise estimate of the effect and a more powerful test of the effect. If it varies, then you can speak about that. Hi, this is Michael Borenstein speaking, and this is the first in a series of lectures on meta-analysis. Our website is www.metaanalysis.com. My email address is michael@metaanalysis.com. And thank you for joining us. Hi, this is Michael Borenstein speaking, and this is the first in a series of lectures on meta-analysis. Our website is www.metaanalysis.com, and my email address is michaelb@metaanalysis.com.